the variety of techniques that we might use to derive or find out exactly where the maximum displacement is, calculate the displacement of the beam out at the end, the momentary method is one. And it turns out to be fairly straightforward, but fairly straightforward doesn't always mean easy. There are some little wrinkles that come along that make this sometimes challenging also. And that's the reason why we have about 20 different ways to calculate the deflection of a beam, because there's always some sort of more difficult scenario out there. So what we're going to focus on right now is how to work with this moment diagram that turns out to be simple yet also tricky and difficult. This shape that we have that we found from beam statics is the second order shape, indicating we've got positive bending moment or smiley face curvature, concave up, over in this left hand region, and then over this right hand region we've got the negative moment or frowny face, kind of concave down curvature. Right? And the support is located right here at this peak, as well as over here at the left edge at A. Right? So what I want you to do is to think about this as how we can decompose this complex moment diagram into a series of pieces that we understand pretty well. For instance, this middle portion is second order, all positive. It is symmetric about its maximum, and that's going to make that really convenient and easy to work with if we do so in that little small piece. Right? This outer hand portion, A2, is also second order with a vertex right up here at the far right, zero slope right there. Right? Vertex is where the slope is zero. And that's going to be an easy one for us to work with too. But this little portion in here, that's going to be not so easy. So let's work with A1 and A2 first, and then we'll come back and talk about what to do and how to deconstruct this little tricky portion here, because it's really that portion that makes this difficult to work with. Right? So you'll note that I calculated the area 1, all of this area, as 2/3 of that base times that height. Well, now where the heck did I get that kind of formula? And that just goes from your typical tables of geometric properties of areas. Right? You know the triangle, 1/2 the base times the height. You know the centroid is at the 1/3, 2/3 location. And if you have a parabola, well, we've got some formulas, but there's special formulas. So you see here a semi-parabola, and then you see down here a parabolic spandrel. These two really fit together. The spandrel is really the other portion of this rectangle, so it's that little skinny portion, and the semi-parabola portion is the big portion that we've got here. Spandrel being the skinny portion, and the parabola being the other portion. Right? So let's actually talk about the parabolic spandrel first. Right? Now, a key thing here is that this thing is some function of x squared. Not plus x term plus a constant term, nope, just the plus x squared term only. A general spandrel would be one that is spandrel of nth degree curve. That means this is x to the nth power. Again, no other terms involved, just that one in the polynomial expression of those two things. And when that happens, we have some really nice, easy to work with formulas associated with both the area for that thing as well as where the centroid of it is located. So for us in this parabolic spandrel, notice that the area is equal to 1/3 base times height. Notice the pattern here. For a triangle, it was 1/2 base height. Right? So a triangle is a first order curve. Increase the order of that curve by 1 and you get a half, or 2 really, right? And so there's your 1/2 base height. It's a second order curve, so now we're going to increase that second order by 1 to 3 and take base times height and divide by 3. Remember, base times height is just the rectangle of this whole thing. And that's why this spandrel up, or the semi-parabola up here, is 2/3 base height, because you've got this thing here that is 1/3, you got the whole rectangle, which is just the base height, you're left over with 2/3. That's the way they work, and it's a really nice little convenient thing. Similarly, when you're talking about these centroids of this piece, the skinny piece, notice we go from 1/3 in the area, and then the centroid goes to a 1/4. That's really cool. Notice again how this worked. For a triangle, we went 1/2 to 1/3 for the centroid, area to centroid. Here 1/3 to 1/4. If this was a 5th degree spandrel, then 5th degree becomes 1/6 for the area, the centroid 1/7. Really cool. That's what the fancy formula down here is really telling you here. right? Notice that n+1 business and that n+2 business that's going on. Really cool stuff, and works out for us really well. Right, so now what we want to do is go back to here. We've got the big portion. Yeah, we've got both of these, right? They're symmetric, so I lumped them all as to one, so that's why it's 2/3 of this entire base times the height, and the centroid is obviously right in the center. Right, now when you go to A2, you'd have then 1/3, because we're the skinny part now, not the big part, but the skinny part, and you've got then the base of 10 feet times then the height of a -6 kip foot for the moment, right? And the centroid there is at the 1/4 3/4 part. I've got the 3/4 actually dimensioned here, so hence the 7.5. Right, and that's how you can work with those two areas. Well, that was the easy part. Now the tricky part, right? This little piece up in here, well, it's a second order curve, but we have to figure out where its vertex is, and it's not really over here at the far left unless you draw a tangent to there, and then it's a skewed little second order portion, right? So we have to cut out this portion, decompose this whole area into two pieces, get that slope through here, that tangent to that curve that divides it into two pieces. One is just the obvious triangle portion, right? And so if I know the slope, which is given to me by the shear value right here, this is right at the inflection point, right? So that's a -1.6 kip foot per foot for the slope, multiplied by the 3.33 feet. Now I know how far it has dropped, right? And if that's larger than the 6, I know I made a calculation here, right? Because that's a decomposing this down, right? So there's your -5.33. The leftover from the 6 has to be then what the second order piece is, right? And so that's why you see this A'3 is 1/2 of the base at 3.33 times the height of -5.33. And then the second part, which is the A3 double prime, is again now it's a second order skinny thing that has a tangent back here at the left, 3.33 feet for the base times 0.67 for its height. And remember, this is just like a triangle. You can skew the triangle and the formula still works, right? And then the centroid will still be that 1/4 3/4 business, just like this triangle is at the 1/3 2/3 location. Now if we wanted the centroid vertically, all bets would be off for the skewed one, but we don't really care about that. We only care about where the centroid is located, left and right. Okay, so that's one way that we could handle and work with this complicated moment diagram. Right? There's another way to do that, and that's what we'll do as an alternative in the next